Hi everyone, this is the second of the loci of complex numbers that we're going to deal with. This time we have a modulus and we don't have a comparison with a different set of points, just with a fixed constant here. So once again we could think about this geometrically, in which case I will write this as z minus 3 plus I is less than 4. I should have said the mod of z minus 3 plus I. So effectively this means the distance between 2 points. And that point there we could mark on our complex plane, 3 plus I. 1, 2, 3. There it is. And we need to locate all points on the plane which are less than 4 units away from this point. Well, everything that's 4 units away from that point sounds a bit like a circle to me. Because the inequality is just less than, does not include equals to, I'll use a dashed line. That's not very accurate. I should be further over there, shouldn't I? Let me try that. Oh dear, dropped the pencil. Having trouble here on this one. Fix this up for you. So let's try this again. If I'm 4 units away, I'd have to end up over there. Once again, dashed line because inequality does not include equals, and we're interested in points where the distance between our point and this spot is less than 4. In other words, we're interested in places which are inside this circle. A fairly simple geometrical argument. Let's see what we'd do if we needed a bit more analytic argument, some algebra. Once again, we will use the fact that our complex number is x plus y times I, and we'll write this into the expression we were given. Now, the real part would be x minus 3. The imaginary part y minus 1. Then the modulus means to square the real part, square the imaginary part, all to the power half is less than 4. Almost there. Now I could put this as 16, or I could write it as 4 squared. I hope you recognise this is the equation of a circle. The centre point of the circle would be at coordinate 3, 1, and the radius of the circle would be 4. So again, we'll get exactly the same result we had last time, of course. The centre point at 3, 1, radius of 4. The inequality does not include equals, so it's a dashed line. And we're interested in points which are less than 4 units away. Once again, it's the inside of the circle. Now, in GeoGebra, I could use a bit of tech to do this. I've already marked my centre point here at 3, 2, and I could, of course, just get my keyboard out. Now, hopefully I'll be a little quicker than last time. I suddenly realised there was an x and a y here on this numeric keypad. Isn't that handy? So I had x take 3 squared plus y take 1 squared. Oh, I somehow managed to have ruined that, haven't I? The squared should be there, equals 4 squared, or 16. Sorry, not equals, less than 16. Enter. There it is, and lovely dashed circle shading on the inside. just the same as we thought when we were working it out here algebraically. Nice and simple. So if we do have an equation that looks like this, it's equivalent to the equation of a circle. And it didn't take terribly much algebra to show the equivalence between those two forms. That's it for now. The next instalment will be about arguments of complex numbers.